Welcome to Study Loop.
Hello there, this is Josh. We're going to be looking at this problem 44-1. So we have a pion that decays into two gamma rays, or gamma photons. Now, it's important to note that when we are dealing with this, the mass, and photons do not have a rest mass, but they do have energy. So let's go ahead and look at this. So we can start here. Here's our pion, and it decays into, let's write this as 2 gamma. All right. The first part of the question asks about the energy. Now, we do have energy conservation. The rest mass is, in terms of the electron, is 270 times the rest mass of an electron. All right. Now, the rest mass of an electron is equal to, generally, we would say this 0.511 keV, or excuse me, 0.511 MeV per c squared. 0.511 MeV per c squared. Now, a lot of folks just get sloppy in their modern units. Mass is MeV per c squared, momentum is MeV per c, and energy is simply MeV. It's in units of electrons volts. So, okay, let's look at this. The rest mass then is simply going to be 137.97 MeV per c squared. Okay, now we're going to assume that both gamma photons here get the same amount of energy. So then the energy is simply the rest mass divided by 2 times c squared, because these are moving at the speed of light. So we have 137.97 MeV per c squared divided by 2 times c squared. And those are going to cancel, okay? So our energy then per photon is 68.985 if we keep all the values here. Mega electron volts. Okay, the next part in this problem deals with frequency. Now, from Einstein's work, we know that the energy of a photon is equal to Planck's constant times the frequency f. Now, in some textbooks, you're going to see this as the Greek symbol nu, which looks like that, okay? But for sake of clarity, really, I think it's better to write this frequency as simply f, but in some older books, you'll see that as nu. It looks like a v, but it is a Greek symbol nu, N-U. Okay, so we can simply rearrange this and get that frequency is equal to the energy divided by Planck's constant. Okay, now Planck's constant in modern units, I'll write out here. If you are ever unsure, you can simply look it up in the table. Now, don't get confused. I've left this as mega electron volts. This is 68.985 times 10 to the 6 electron volts. So in our calculations, be sure to do that. And Planck's constant in these units is 1.63. Oops, excuse me. That is the, let's look here. We are 4.1357 times 10 to the minus 15 EV times second. Now notice this M just means times 10 to the 6, okay? So we could simply change this on the top so that it's all in electron volts to say times 10 to the 6 electron volts. Now, what does this mean? Electron volts on the top and bottom cancel, and we're left with seconds on the bottom. Frequency is 1 over second, or hertz. So when we solve this out, we get that this is equal to 1.67 times 10 to the 22nd hertz, or otherwise a very high frequency. All right, now let's think about this physically. If I have a very high frequency, I have a very small wavelength. And the relation for wavelength is generally noted as lambda. So wavelength is equal to your velocity divided by the frequency, but this is a photon. And we assume we're in vacuum, so c, which is the speed of light in a vacuum, divided by f. Okay. Now c is equal to 2.99 times 10 to the 8th meters per second, divided by the frequency of our previous problem. Now note we have meters per second on the top and frequencies in hertz are 1 over a second on the bottom, so we're going to be left with meters, which physically makes sense. A wavelength is the distance from one wave to the next. 1.79 times 10 to the minus 14 meters. Okay, now what part of the electromagnetic spectrum is this in? Simple. This is a gamma ray, very energetic. Thanks.